Okay, are you ready to begin, Dmitrii?
Yep.
Okay, welcome back, everybody, for the final talk of the morning. So Dmitrii Pirozhkov is going to tell us about admissible subcategories of P2. Thank you.
Okay, thank you for the invitation to speak on this workshop. So I will speak about admissible subcategories of the projective plane, and maybe I will also say something about del Pezzo surfaces, depending on how much time we will have at the end. Okay, so before I start, let me just indicate what kind of things I'm going to talk about. So this research is about bounded derived categories of coherent sheaves. So given an algebraic variety, we form this category basically out of complexes, and it can be considered as a huge invariant of the variety. So it contains a lot of information, and many smaller invariants can be recovered, like algebraic theory or Hochschild homology or other things. So this indicates that maybe studying derived categories of coherent sheaves is a good idea if you want to study other invariants as well. So the word admissible in the title of my talk is defined as follows. If I have a full subcategory of my bounded derived category of coherent sheaves, and everywhere where I say category or subcategory, I mean triangulated categories and subcategories as well. So a full subcategory is called admissible if its inclusion functor has both left adjoint and the right adjoint. This definition is quite categorical, and we will see some reasons why we are interested in such subcategories a bit later. Another important notion is a semi-orthogonal decomposition of a category. I will not use this very deeply in my talk, but basically this is just a collection of admissible subcategories which not only generate the entire derived category, but also do this in a certain minimal way that's guaranteed by the semi-orthogonality. And this is a condition very similar to the one that Sasha Kuznetsov explained yesterday for exceptional collections. And the relation between these two definitions is that as long as we work with smooth proper things, any admissible subcategory leads to a semi-orthogonal decomposition when we take a certain orthogonal left or right subcategory as the other component. So understanding what kind of admissible subcategories are there is roughly equivalent to understanding what kind of semi-orthogonal decompositions exist. Now, these notions are more notably semi-orthogonal decompositions, they let us understand larger categories in terms of their components, which are hopefully smaller or more understandable categories. Or maybe they are related to the varieties which we understand better than the ones that we started with. So, a very rough overview is that we know very many examples of semi-orthogonal decompositions, and we also have many tools of various complexity that can be used to produce new examples, starting from old ones. So as for examples, here are a few standard ones. For example, if you have a smooth projective variety X, and you take a blow up of a smooth subvariety and call that Y, then you have this pullback functor from the derived category of sheaves on X to the derived category of sheaves on Y. And it turned out that this functor is fully faithful, so it is an embedding of a subcategory. And moreover, it has both left and right adjoints, which means that the subcategory, which is the image of the pullback, is not just a random subcategory, but in fact admissible. And other sources of admissible subcategories come from exceptional collections. Basically, you take a subcategory generated by an arbitrary subcollection, and it will be admissible as well. And I think Sasha Kuznetsov explained yesterday how to construct those adjoint functors to the inclusion of the category. And there are other probably deeper ways to produce semi-orthogonal decompositions. However, even though we know many examples, we don't really have a good grasp on general properties of what kind of semi-orthogonal decompositions may exist. Even if we'll look on a very familiar variety like a projective space, then of course we know many semi-orthogonal decompositions arising from exceptional objects, for example, but we don't really know what other kind of decompositions exist. So we don't have a good structural theory that will tell us what can happen and what cannot. And in my talk, I will be mostly working from this point of view that we want to understand at least something general. So as I've said that we don't really understand structure of possible semi-orthogonal decompositions, or equivalently structure of possible admissible subcategories. So to kind of clarify what I mean, I'll just give a couple of open questions, which I think no one knows how to solve yet. Just to give you a taste of what kind of things we do not know. Even though the definition of an admissible subcategory is so simple, just an inclusion that has both left and right adjoints, we don't, for example, know this conjecture by Sasha Kuznetsov that if we have a smooth proper variety and we have an increasing chain of admissible subcategories, then it should stabilize at some point. So some kind of noetherianity condition, and we don't know how to prove this. And other example of a open question is that if you have an admissible subcategory in the derived category of some variety, sometimes it happens that this admissible subcategory is not just triangulated category with some structure, but in fact maybe identified with a derived category of sheaves on something else, like on some other variety Y. And then the expectation is that you should not have an admissible subcategory which is equivalent to the derived category of higher dimensional algebraic variety. So it's just to illustrate that we don't really have good tools to control the behavior of admissible subcategories. And there are many other open questions, like for example, many questions about phantom subcategories that were mentioned today, and but I will maybe mention them as we come closer. Now, there are some easy cases where we can actually say a lot about the behavior of arbitrary admissible subcategories. And there are kind of two groups of situations. The first one is that there are many varieties for which we know that there are just no non-trivial admissible subcategories at all. So if a triangulated subcategory is admissible, then it is either just zero or the entire category. This happens when X is Calabi-Yau, or more generally, if its canonical bundle is globally generated. So curves of positive genus do not have any admissible subcategories, or in other words, no semi-orthogonal decompositions. They are indecomposable, if you want. And and the other case is projective line. Here we can actually classify all possible admissible subcategories, and the answer is that any non-trivial admissible subcategory is generated by a single line bundle. So O of n for some n. And this is kind of easy to do, mostly because of this, I think it's called gross index splitting theorem, that there are no non-trivial vector bundles on P1, just everything splits into line bundles, and you can just work with this description a bit to classify admissible subcategories. And I want to sketch a full classification for admissible subcategories in a derived category of sheaves on P2. So it extends the list that I outlined with another example, which is less trivial than P1. So there are many options, but it is possible to show that there are no other exotic options that we have not seen before. Okay, and one property, general property of admissible subcategories that we know, and that is in fact quite easy to show, is the following topological rigidity property. It's proved by Kawatani and Takawa in their paper that was mostly dedicated to studying which varieties have indecomposable derived categories, but along the way they developed this interesting tool that is quite convenient. So they proved that if you have a smooth and proper variety and you have an admissible subcategory in its derived category, then automatically this admissible subcategory is closed under small deformations of objects, in the sense that if you have a family of objects in the derived category and the central fiber, I mean, some object from this family lies in the admissible subcategory, then you have a risky open neighborhood of the base of the family for which all of them just also lie in that admissible subcategory. And another small amplification of this result of this statement is that, in fact, admissible subcategories are closed under the action of the connected component of the automorphism group of your variety. So this is almost the same as just being closed under small deformations, but you need to include the entire group instead of just some neighborhood of the identity element. So, this theorem is not hard to prove. It basically shows that the property that some object lies in admissible subcategory can be rephrased in terms of vanishing of certain X groups. And then you use semi-continuity of the dimensions for X groups. This is a bit surprising, I think, because the definition of admissible subcategories is purely categorical and has nothing to do with deformations. But somehow, as soon as you work with smooth proper varieties, you, for free, you get this kind of deformation invariance for free. Another way to interpret this result is that if you have an admissible subcategory, then it is kind of, you cannot deform the subcategory inside the derived category of X, because kind of small deformations of any objects are already included. So kind of the set of admissible subcategories does not form any kind of moduli space. It's just a discrete set, that also makes it hard to classify the options. All right. So, are there any questions so far? Okay, I guess I'll continue. So now I will start speaking about the case of projective plane and how can we study admissible subcategories of the projective plane. So here is one approach. So suppose you have an admissible subcategory called curly B in the projective plane. So let's take some point P on the plane. We take a skyscraper sheaf at that point and take the projection of this sheaf into subcategory B. I guess I did not formally define what a projection is, but my definition of an admissible subcategory was that the inclusion functor has left and right adjoints, and you can check that those adjoints are projections, in the sense that if you include an object and then project it, then you just get the same object back. And for example, I call the right adjoint to the inclusion functor as a right projection. And I denote it as follows, as this curly B with index R. So so overall, I take a skyscraper, I project it to my subcategory B. I call this just Roman B. And here are a few observations about the subject. First of all, it will be invariant under the action of the subgroup of PGL3, which stabilizes this point. And second, perhaps more importantly, is that this single object B, in fact, uniquely determines my admissible subcategory. So, first I'll briefly say why this should be true. Mostly it all follows from the Kawatani-Akawa theorem, because PGL3 is the connected, well, the automorphism group of P2 is PGL3 and it is connected. And therefore, our subcategory curly B is invariant under the action of PGL3. And this these projection functors as adjoint functors to inclusions, they have some universal property. And it formally follows from the universal property that if instead of taking a skyscraper at the point P, you take some automorphism called G, take the pullback along the G, which will be just a skyscraper at some different point, and take the projection, then you can understand the result in terms of this straight B. So that's a sketch. You can do this formally, but the upshot is that if this small g stabilizes the point P, then the left-hand side does not change. It's still the projection of the skyscraper at P, and therefore the right side should also be isomorphic to B, which establishes the first claim. And similarly, if you know this isomorphism, then you know how the projections of then for any skyscraper, you know how the projection of the skyscraper to curly B looks like. And it is not hard to see that if you know the projections of all skyscrapers, then you essentially know the projection of everything, and you can recover curly B. If you want a specific recipe, then you take kind of this how to determine the category curly B from the object Roman B. You take the PGL orbit of this Roman B, so just pullbacks along all automorphisms from the stabilizer subgroup, and then take the, for example, left orthogonal to the right orthogonal to this set of objects, and this will be your curly B. But the recipe doesn't really matter. It just the key thing is that you can recover, you can determine your admissible subcategory if you just know this projection of the skyscraper as this single object. So we can perhaps attempt to study what kind of admissible subcategories are there by just trying to see which objects could theoretically be projections of the skyscraper sheaf. So, but how can we do this? This is not clear normally, because projections of arbitrary objects in the derived category are very hard to understand. I mean, if you don't know what kind of admissible subcategories are there, you don't really know what kind of projections do you get. But skyscrapers are quite special objects. In particular, if you just take some subvariety of P2, for example, some curve that passes through the point P, then the skyscraper sheaf at the point P may be viewed as a push forward of something from that curve. So right now, it is not clear why this helps. And to see why this is useful, I will introduce an important theorem by Nicholas Eddington that is the key technical statement in my argument. So first, I will give the actual statement in terms of spherical functors. But since I don't really rely on any non-trivial properties of spherical functors later, I will actually use only the following corollary, which does not use this notion. So if you know what a spherical functor is, then the theorem sounds as follows. If you have a smooth and projective variety X and some admissible subcategory curly B, then for any anti-canonical divisor called J, it is well known and easy to show that if you just take the restriction functor from sheaves on X to sheaves on D, then this is a spherical functor, and Eddington proved that when D is anti-canonical, then this composition with an embedding of an admissible subcategory is also spherical. So I won't use this statement, as I said. So I'll just use the following corollary. So it concerns the projection functor. So this right adjoint to the embedding of the subcategory. It sounds as follows. Given an arbitrary object F, which is a perfect complex on D, I guess, so if D is smooth, then perfect complexes are the same as just bounded complexes of coherent sheaves. So don't worry about that. So if you have an object like this called F, then there is always a functorial triangle in the category, in the derived category of D, where the object in the middle is just our original F, and the object on the left can be obtained by the following operation. You take the push forward to get an object on your variety X. Then you use your projection functor BR to get some object in the admissible subcategory curly B on X, and then you restrict back to the divisor D. There is a natural map like this, coming just from a junction. And the content of the corollary is that the cone of this map is not just some random object in the derived category, it can be obtained by applying some autoequivalence to the object F. So this sounds a bit convoluted, so let me unwind this a bit. So here is the same corollary as on the previous slide. So the thing is, autoequivalences of derived categories are, they're easier to control than arbitrary admissible subcategories, because an autoequivalence is a very concrete thing. So you can think about, for example, where should a skyscraper sheaf go, where should a structure sheaf go, and so on. It is not trivial to determine the autoequivalence group, but sometimes this this has been done. Now, if we want to understand the object like this, where, I mean, we take push forward of something from our divisor and take the projection functor to curly B. Then, if you also know a lot about autoequivalences of that may arise as this T in the statement, then the triangle above may be useful. So we don't get a direct information about the projection of the push forward of F, but we at least get something about the restriction of this projection back to the anti-canonical divisor. So this is some very indirect, very partial information, but still it's kind of better than nothing. And in fact, what we want to do is exactly that on the projective plane. We want to study the projection of the skyscraper sheaves. And the anti-canonical divisors in P2 are just elliptic curves. And it so happens that autoequivalences of elliptic curves are very well studied. And there is, I believe, a full determination now. And for smooth ones, it's relatively easy. And if you really care about singular ones, you need to work harder. But I believe that this is known as of 2020. And we will only need smooth case anyway. So we know a lot about these autoequivalences, and we want to study the projection of the skyscraper sheaf. But this skyscraper sheaf can be considered as just a push forward from any smooth cubic curve passing through the point P. So we, even though we only, from this corollary on the top of the slide, we see just a tiny indirect piece of information, we have a lot of freedom. Because, for example, we can apply this to an arbitrary cubic curve passing through the point P and just look at all these restrictions simultaneously and just try to piece together this information. So, moreover, if we are on a surface, which is the case where we work on, then the anti-canonical divisor is always an elliptic curve, and we can say something stronger. So, so assume we have our X as a surface. Then we take a smooth anti-canonical curve D, we pick some arbitrary point on this smooth curve, and again consider the projection of the skyscraper sheaf, and we get a distinguished triangle like this. So this is a distinguished triangle from the corollary above, but we just use this T index P as a notation for this autoequivalence T applied to a skyscraper. Now, since T is an autoequivalence, at the very least, we know that the endomorphisms or derived endomorphisms, which are just self-X of this object TP, should be the same as for the skyscraper sheaf, since T is an equivalence of categories. But already this is an extremely strong condition on the object TP. Namely, it is not hard to see, to prove the following lemma, that if we have any kind of skyscraper-like object, where skyscraper-like for me just means that the X algebra looks like the X algebra of the skyscraper. And it's a skyscraper-like object on a smooth curve, sorry, on a smooth elliptic curve, I guess, or no, that probably shouldn't matter, but I'll only apply this on smooth elliptic curves, is there are just two options. Up to a shift in the derived category, this is either an actual skyscraper sheaf, possibly at some other point, maybe not at P, we don't know. Or it can be a single simple vector bundle, again, shifted to an arbitrary degree. In fact, for the case of Pezzo surfaces, I'll need something stronger, which is kind of the same result, but for irreducible reduced curves instead of smooth curves. And it is harder, of course, but also no. Okay, so this lemma tells us that when we want to use the approach I've sketched, where we just apply Eddington's theorem to everywhere we can, we get the following conclusion that that on a surface, this if you do the same things and you consider this object Roman B, then whenever you restrict it to a smooth anti-canonical divisor, it will be an object that is either built out of two skyscrapers, where built just means is isomorphic to a cone of a map between two skyscrapers with possibly shifts, or it is built out of a single skyscraper and a single simple vector bundle, where again built has this meaning that it is a cone of a map in the derived category. So this is a surprisingly strong structural result, because this, for example, implies that this restriction B to D has at most two cohomology sheaves. One problem that we get stuck if we want to work with arbitrary admissible subcategories is that we need to kind of the projection of the skyscraper in principle could be an arbitrary complicated complex. So it can have a huge amount of non-trivial cohomology sheaves, and it is hard to work with such objects. But at least now we see that when we restrict to anti-canonical divisors, we don't get too complicated objects in the derived category. And another observation, which is also kind of tautological, is that if this restriction to D is not a torsion object, by that I mean it is not supported just on finite set of points, then we immediately conclude then that the class in the Grothendieck group of this restriction is non-zero on the elliptic curve, because you can detect the classes in K0 by just taking arbitrary alternating sums of ranks of cohomology sheaves. So this is kind of a rank of a vector bundle, but extrapolated to the entire derived category rather than coherent sheaves. And since our object B is built out of a skyscraper and one vector bundle, we will never get zero. Well, unless the vector bundle itself was zero, but that's a simple case. All right, so we will come to this observation later, but this is kind of an immediate implication that we get from Eddington's approach. And let me use it to prove that for any admissible subcategory in the projective plane, the Grothendieck group of this curly B can never be zero unless the category is zero itself. So as mentioned by Sasha Kuznetsov, you can phrase this result by saying that there are no phantoms in projective plane, where a phantom subcategory is defined to be a non-zero admissible subcategory with vanishing Grothendieck group. All right, so well, how can we do this? So we just follow the same strategies that I outlined. So pick some point P, take a Roman B to be the projection of the skyscraper, and from the and this is a kind of looking at this projection of the skyscraper is a reasonable tool to study admissible subcategories in P2 by the lemma above, which among other things proves that the object B is invariant under this large group of automorphisms of P2 which stabilize the point. Because the skyscraper sheaf was invariant under this group, so the projection is as well. Now, this group has only two orbits, just the point and everything else. And so there are three possible options for the subset support of B. Now here, support is just set theoretical notion, so a union of set theoretical supports of all cohomology sheaves. There are no good scheme theoretical. There is no good scheme theoretical notion of a support for objects in the derived category, but I am not speaking about that, just said theoretically. So the first case is, what if the support of the object is empty? So this implies that the object Roman B is equal to zero. And you can relatively easily see that this implies that the entire admissible subcategory B must be zero. And that's a simple case. The other case is, what if the support of B is a single point P? Well, it is slightly less trivial, but you can also conclude, operating purely on Kawatani-Okawa theorem, that this implies that the subcategory curl B is the entire derived category of P2. So that's also not an interesting case. And the only non-trivial case is when the support of the object B is a whole projective plane. Okay, so why is this useful? So now we apply the approach. So we pick some smooth cubic curve D passing through that point, and then D is an anti-canonical divisor of P2. So for the restriction B to this anti-canonical divisor, we can apply the method. Sorry, I guess that's it was called method of section 2, where section 2 was the part where I started to discuss addiction theorem. Sorry. So since the support of the object B was the whole projective plane, then the support of the restriction will also be the whole curve D. So now we know that this restriction of B to this divisor cannot be built out of two skyscrapers because the support is full. So it is built out of a skyscraper and a simple vector bundle. And this implies that there is exactly one cohomology sheaf which has non-zero rank. And as I have mentioned previously, this implies that the class of this restriction is not zero in the Grothendieck group of sheaves on this smooth elliptic curve. And but since the class of the restriction is the image of the class of B under the restriction homomorphism of Grothendieck groups, this implies that the class of B in Grothendieck group of P2 is not zero. And that's it. So we have just explicitly constructed an object Roman B in our admissible subcategory curly B, which has non-zero class in the Grothendieck group. So this proves this thing that I claimed, that there are no phantoms in P2. So that's already a quite non-trivial result. Sorry, other questions in the chat? Yeah, so for a fixed admissible subcategory, I can look at a single point P without varying the points at all because of that lemma above. That if I take that the projection of a single skyscraper sheaf actually determines everything, and if you look at the projection of skyscraper sheaf at some other point, then you just pick some automorphism from PGL3, which moves one point to another and takes the pullback of this object Roman B. Yeah. Okay. So any other questions? Okay, so all right. So well, this proves that there are no very strange admissible subcategories in the derived category of P2, but I have announced the full classification, and somehow the key thing over here is that at this step, we know that when we restrict B to the cubic curve D, we know that it is built out of a skyscraper and some simple vector bundle on this smooth elliptic curve. But we know this for an arbitrary elliptic curve passing through the point P. So kind of for an arbitrary cubic curve, we get this vector bundle on it. And with some work, you can check that basically all those simple vector bundles that you get on cubic curves, they have kind of common ancestor, which is a vector bundle on P2. And you can also kind of build upon this observation to show that this vector bundle will be exceptional, and then you kind of bootstrap from here to get a full classification. So let me just give the statement of this. So with some additional work that I very hand-wavingly sketched, the result may be improved to a complete classification that any admissible subcategory is one of the known, one of the classically known examples of admissible subcategories in P2. So by that I mean it comes from a full exceptional collection of P2. And explicitly, there exists some full exceptional collection E1, E2, E3, which can be obtained from the standard collection, which is collection O of 1, O of 2, constructed by Beilinson a long time ago, by a sequence of mutations, which are some operations that Pirozhkov explained yesterday, which kind of transform one exceptional collection into some other ones. And basically, we start with a standard collection, we take some mutations, and then we take a subcollection of this sequence. And you can get all admissible subcategories by this approach. And kind of the idea of the proof, besides the thing that I have already mentioned, the kind of key step that uses the very special behavior of P2 is that given some admissible subcategory A, as I mentioned, you can also form an orthogonal subcategory A perp. And then you get a semi-orthogonal decomposition of your derived category with these two components. But if we believe the theorem, then this semi-orthogonal decomposition into curly A and curly A perp is obtained by just subdividing some full exceptional collection. And it's a special property of number 3 that if you divide it in any non-trivial way, then at least one of the components, then exactly one of the pieces will contain just exactly one exceptional bundle. So this lets you try to guess which of the categories A and A perp is kind of simpler, and then you do various deductions that rely on those simple vector bundles you get when restricted to any cubic curves to show that the category that looks simpler is in fact generated by a single exceptional vector bundle. And then kind of you get the full classification for free because exceptional collections and exceptional vector bundles were classified on P2 a long time ago by Grodientsev and Rudakov. So I guess a couple of words about this is that if you kind of even wanted to do something like this on Pezzo surfaces, even if it assumes that all previous parts work without any modifications, then, well, we do have some classification of exceptional collections and exceptional objects by Rudakov and Orlov, I believe. But still, this very first part, where I just try to guess which of the components is generated by a single vector bundle, will not work because on Pezzo surfaces, the exceptional collections are longer. So you need perhaps some more subtle argument instead of just this brute force observation. Okay, right. Are there any questions about this?
Are there examples of varieties with full exceptional collections and admissible subcategories that are not generated by
yes, there are examples. For instance, those examples of those phantom categories that were mentioned by Sasha Kuznetsov. One of them works as follows: you have some surface whose derived category has a full exception collection with 11 objects. And there is a different exception collection which only has 9 objects, and the orthogonal part, which will be admissible, cannot be split into 2 exceptional objects. It's kind of indecomposable and does not split like this. So this may, in principle, happen.
Thank you.
And I guess more generally, we know that we cannot expect any kind of Jordan-Golder filtration claims about semi-orthogonal decompositions. So it is not true that given arbitrary 2 decompositions, you can kind of refine both of them to get the same components. This is not true, and this is not true.
Thank you.
Okay, other questions? So if not, then I'll say something about the case of, sorry. Yes, there is a question in the chat This counterexample does not have a movable anti-canonical class and does not have a good transitive action. So it is possible that whenever you have a transitive action of a group, that is to say, when your variety is homogeneous in the sense of the talk given today by Sasha, then probably there shouldn't be any counterexamples, but we don't know. So the argument that I sketched relies on the action of the group G, but in fact, for this particular case of P2, you can get rid of most instances of symmetry by just varying the cubic curves and taking a general enough cubic curve instead of using the group action. But that also is not available. But you're right that having this movable anti-canonical class lets us extract a lot of information from these restrictions to anti-canonical divisors. And this is why we can do at least something for the Pezzo surface. So first, I will give a picture of what is a rational elliptic surface, because that's a actual geometric object that I work. The definition is simple. It is some surface S such that the anti-canonical linear system gives you a regular map to P1. So that some map to P1 whose fibers are exactly anti-canonical divisors of S. General fiber is a smooth elliptic curve. And we also work only with the case where sections exist, and they all happen to be -1 curves in our surface S by just adjunctive formula, because it's a section of the anti-canonical fibration. Now, what happens if we try to do the same thing as we did for P2? I mean, this non-existence of phantoms. So assume we take some point P. Again, take a Roman B to be the projection of the skyscraper sheaf to some admissible subcategory, which we fixed. This point P lies on a unique anti-canonical divisor J. It is unique because of the picture I've given, because anti-canonical divisors are just fibers. So each point lies on a unique anti-canonical divisor. Now we can also try to consider the pullback of this Roman B to this fiber and try to use the same argument as for P2 to attempt to conclude that the class of this Roman B is not 0 in the Grothendieck group. Now, the thing that breaks is the very simple, is the very beginning, where I mentioned that on P2, the support of this object Roman P was one of 3 options, and all options except the entire P2 were just trivial to deal with. And now this will not be true. So the same proof for non-existence of phantoms works unless this restriction is built out of 2 skyscrapers, which happens when the support of B, the set theoretic support, is some subset of the surface which intersects the fiber in just finitely many points. This is a case that we never saw for P2 because we had this action of the group that told us that this is impossible. But for rational elliptic surfaces, this actually happens. But if the under the additional assumption that the fibration pi has no reducible fibers, this roughly corresponds to this lemma about skyscraper-like objects and curves. As I've said, that if you have an object on a irreducible curve whose X algebra looks like X algebra of a skyscraper at a smooth point, then you have a classification which looks the same as in the smooth case. So this case can be studied explicitly, and in fact, nothing exotic really appears. All the cases where the support of Roman B is not the entire surface S, they appear from a very well-known exceptional, very well-known semi-orthogonal decompositions that arise because a section is, the sections of the map pi are -1 curves, and -1 curves can be blown down, and there is a semi-orthogonal decomposition for semi-orthogonal decomposition formula for a blow-up. So you can prove that nothing except this actually happens in this range of cases where this restriction of B is built out of 2 skyscrapers. So, and this is much more difficult than what we did for P2, and we kind of heavily rely on this restrictions to anti-canonical divisors and their properties. But this can be done, under the assumption that the fibration pi has no reducible fibers. So, for example, for a rational elliptic surface without reducible fibers, this proves that there are no phantom subcategories. And with a simple geometric argument, you can reduce the case of del Pezzo surfaces by blowing up some general points to this particular case. And this also shows that del Pezzo surfaces do not have phantom subcategories. That's it. Thank you for your attention.
All right, let's thank Dmitrii. Any questions for Dmitrii?
I have a question.
Uh-huh.
If we dispense with, I guess, Addington's theorem, and I look at a curve that's not anti-canonical, say like a line or a conic in P2, is there any hope I can still analyze, like somehow run the same program for those curves, even though they're not anti-canonical?
I don't think you can get a lot of information because we used the fact that the curve was anti-canonical to kind of deduce that, let me get back to the statement, that in this corollary, we have this functor t, and it always can be defined as a cone of the map. But in general, we don't have any information about what kind of functor this is.
Is it because it's false, or just we don't know how to prove it?
Well, it is false that this will be an autoequivalence.
I see.
Maybe in some cases we can say something about this functor t, but it's difficult.
Okay, thank you.
You're welcome.
Okay. Can I ask?
Sure.
Please.
Hello? So yeah. So what about P3?
Okay, that's a very interesting question. So we can try to apply the same methods, but for curves, as I mentioned here, autoequivalences of elliptic curves are known, but that's not the full story. The full story is that not only they're known, they're all very simple and very clear to understand. If we want to do this for P3, we will have to restrict to quartic case-free surfaces. And in fact, for a general quartic case-free surface, the group of autoequivalences of the derived category is also known. But the description is quite complicated. And in particular, over here, we had this lemma that basically told us that when we apply autoequivalences to skyscraper sheaves, we don't get too complicated objects. But on case-free surfaces, there are autoequivalences which are kind of squares of spherical twists along some, with respect to some spherical bundles. And it is very hard to control what kind of objects do we get. So the answer basically is that, for example, here on this slide, we got this immediate non-vanishing of the class in the gross-ending group as soon as we can assure that we are not just building our object out of two skyscrapers. And this is this step is missing for case-free surfaces. I tried to think about them, but so far I don't know how to do this. But this is very interesting. Thank you for the question.
And so the main issue on carrying this out for, say, P1 cross P1 or F1 or something like this is that 2 + 2 = 4? Or
yeah, I mean, probably the case of P1 cross P1 should be feasible in some way, but I was not able to make it work. Okay. In the step where I prove the full classification, I don't really have kind of given an arbitrary admissible subcategory. I don't really have a way to kind of find exceptional collection inside of it. I just if it is just generated by a single exceptional object, then I just see it and prove it by hand.
Yeah.
But if
That's a problem we've encountered before. We've got sometimes you've got a like on F1 or P1 cross P1, you've got kind of a way of you've got, say, two orthogonal objects or something, but they're made up of maybe two exceptional bundles instead of just a single exceptional bundle. And it's hard to detect what the right exceptional pair is or something like this inside of that.
Yeah.
Are there any other questions? Okay, well, thank you, Dmitrii, for a very interesting talk. Let's thank Dmitrii again.
Thank you for your attention.